remember that a sequence is a list of numbers with commas in between them, as opposed to a series, which we'll talk about later, which is a list of numbers that we're adding together. So a sequence, the formula for our sequence is an is equal to n plus 2 factorial over n factorial. Okay, so are there a question about this one? What are your thoughts on this particular problem? You're like, I see that factorial. Okay, so the first comment here is that this is the formula for each term in our sequence, and our job is to figure out whether this sequence converges or diverges. And if the sequence converges, then we have to figure out what its value is. And it was pointed out to me yesterday or the day before, and I totally agree with this, that the directions say determine whether the sequence converges or diverges, and then if the sequence converges, figure out its value. Well, those are kind of backwards, because in order to figure out whether the sequence converges or diverges, you have to analyze the limit and figure out whether you get a value for the limit or whether you don't. And once you do that, then you've done part B of the question before part A. So our job is to figure out a limit as n goes to infinity of n plus 2 factorial over n factorial. So let's talk about what factorials mean. If I have something such as maybe 4 factorial, these are factorials. If I have 4 factorial, that means that I'm starting at the number 1 and multiplying every whole number until I reach 4. So 4 factorial is a shorthand way of writing 1 times 2 times 3 times 4. And so if I have something like, say, 6 factorial, that's 1 times 2 times 3 times 4 times 5 times 6. Now, there are some strange things that have to do with factorials. And the thing about factorials is if I do something like take 6 factorial divided by 4 factorial, what I am not allowed to do is to say, oh, look, there's a factorial on the top and the bottom and pull it out to the side. Because if I tried to do that, then I would have 6 over 4 and then a factorial. And that actually doesn't make sense because this is a fraction in here. We can't talk about factorials with fractional values. So that's not going to work. So we don't want to do that. But if I do write these out and I expand these, 6 factorial over 4 factorial, I have 1 times 2 times 3 times 4 times 5 times 6 divided by 1 times 2 times 3 times 4. So now when I look at this fraction, notice that things cancel. The 1, 2, 3, and 4 multiplied together cancel on the top and the bottom. And I'm actually left with 5 times 6. And so 6 factorial divided by 4 factorial is actually 30. All right, are there any questions about this example for factorial? Okay, so let's go back to our problem over here. Over here we have n plus 2 factorial divided by n factorial. So if I write this out, n plus 2 factorial divided by n factorial, on the bottom, n factorial says that I'm going to start with 1, and then times 2, times 3, times, and I'm going to keep on going until my very last number, which is going to be n. And on the top, this is the one I want to think about pretty carefully. On the top, I'm going to start out with 1 times 2 times 3, and I'm going to keep on going. And the very, very, very last term that I'm going to get is n plus 2. Now, it's not really clear how I'm going to cancel things out. So if n plus 2 is my last term, what's one number less than n plus 2?
N plus 1. N plus 1?
Yeah, n plus 1. And what number comes right before n plus 1?
N.
Yeah, n. And so my very last 3 terms are n times n plus 1 times n plus 2. All right, so are there any questions about how we've expanded out either the n factorial? Yes?
I'm a little confused on how you're starting out with 1 and 2. It seems to me that the starting number would be 3 or 2 if you started off. with-
For up here?
Yeah, from top.
So whenever you have the factorial, no matter what this number is inside here, you always start with 1. So just like here, even though we started with 6, even though 6 factorial, we started at 1, and 4 factorial, we started at 1.
Okay, thank you.
Okay, other questions? Okay, so now I've got all of these terms with multiplying all these numbers across the top, multiplying all these numbers across the bottom, and a whole bunch of these things cancel. So I can cancel out 1 times 2 times 3 all the way up to n on the top and the bottom. And that leaves me with n plus 1 times n plus 2 all over 1, and I don't need to keep them in the denominator. All right, so this factorial that is used in our sequence here if I expand these terms out and do the canceling like I did up there, then we end up with the limit as n goes to infinity of n plus 1 times n plus 2. So now we've gotten rid of all the factorials and we can analyze this. And notice I have no denominator here whatsoever. So as n gets really big, what happens to n plus 1 times n plus 2?
Goes infinity.
Yeah, this is going to get really big as well. And so our limit is going to be equal to infinity. And so our sequence diverges. Arthur, does that answer your question? Okay, great. Are there any questions about this particular example, number 13? This was a good example to ask about. We're going to see factorials when we work with series throughout the next couple of class periods. And so this was a good sort of get your feet wet with a factorial term. Okay, any other questions out of 8.1?
21?
21?
I mean, I did it, I
have a
just want.
question in general.
Okay.
When you look at that, it's kind of easy to look at the problem.
Yes.
It's kind of easy to tell that the top is bigger than the bottom, even if you don't know all this.
Mm-hmm.
Is that, that's not a viable answer though, is it? Like you could,
You have to be a little bit careful. So once you've done, maybe 10 factorial problems, then you can look at that and say, oh, things are going to cancel. I'm still going to have an n value in the top. I mean, for example, if I have 3,700 n to the 5th over 0.0005 n to the 6th. So looking at the numbers that I see here, there's a very much larger number on top, but in terms of the powers, my power on the bottom is much larger. And so as n goes to infinity, this term is going to go to 0. And so what you really want to focus on is which part of the expression is the large. In other words, what is actually driving the sequence as we get to large n values. And so you're right. Once you've done 10 of these factorial problems, then if you have a larger factorial on the top than you do on the bottom, then you know that the sequence is going to diverge. So yeah. So you can do that, but make sure you justify what you're saying. Okay. So Dennis, you said number 21.
Mm-hmm.
Okay. So number 21. Also in section 8.1, we have an is equal to cosine squared of n over 2 to the n. And our question is, does this sequence converge or diverge? All right, so Dennis, what were your thoughts on this particular example?
Well, I used the squeeze term.
Okay, so this seems like a really good idea. So when we look at these terms, I can see that on the top I've got a cosine function. Now I'm not exactly bouncing between +1 and -1 because cosine of an integer value is going to be some weird number, but it's going to be kind of oscillating and bouncing all over the place. But because it's doing that, that means that I want to think about, okay, that top number, cosine squared of n, is going to be less than or equal to 1 and greater than or equal to -1. So anytime I start to have something that's bouncing all around, I might start to think about using the squeeze theorem. Now, the top part is our bouncing around part, our oscillating part. And the bottom part is just kind of moving on. So as n gets really big, this denominator is getting larger and larger and larger. So the thing that I want to squeeze is the oscillating part. The rest of it, I want to keep exactly as is on all three parts of my squeeze theorem. Okay?
I thought that cosine squared n went between 0 and 1.
That's a good point. So I was totally ignoring this square up here, and so I said, oh, cosine goes between -1 and 1. And we can actually be even stronger and say, okay, this is cosine squared, so it's never going to be a negative value. So we could change this to 0, and that would work as well. Okay, so let's talk about it with the 0 on here and see what happens. So as n gets really big, 0 over 2 to the n still stays at 0. So as n goes to infinity, 0 over 2 to the n goes to 0. And as n goes to infinity, 1 divided by a very large number is very tiny, and so 1 over 2 to the n, as n goes to infinity, 1 over 2 to the n goes to 0. And so that means we've squeezed our term in the middle between two zeros, which means our middle term has been squeezed and also goes to 0. And so our limit, as n goes to infinity, of cosine squared n over 2 to the n is equal to 0. Okay, so now this question about whether we should use 0 or -1, it turns out that 0 is probably the better choice because it's a tighter bound on the bottom. And so 0 over 2 to the n, cosine squared of n is always greater than or equal to 0, so that's totally legitimate. And I was being a little bit sloppy. I was forgetting about that squared part and saying, oh, well, I know that cosine of n, the smallest that can be is -1. And it turns out that -1 over 2 to the n also goes to 0. And so that would have been an okay bound there for us as well. And so the bounds that we use, we just have to guarantee that the number on the right is larger than the middle number, and the number on the left is always smaller than the middle sequence. And as long as the left and the right both converge to the same value, as long as they squeeze the middle one to one single value, we're good to go. So there's not one correct answer here in terms of the squeezing. All right, Dennis, does that answer your question?
Yeah, I use the -1 over 2n, but I wasn't thinking like he was thinking with the 0, that total with the square, but.
Yeah. So either one will work.
Yeah.
Good. Okay, other questions about number 21? All right, so these were both good questions to ask about. All right, so last class, in the first hour, we talked a little bit more about series. And so 8.1 was sequences, and so a sequence is a list of numbers. So we're going to continue with section 8.2, and we're also going to talk about section 8.3 today. So we're going to continue focusing on series. So our sequence is a list of numbers. Let's see, what am I looking at here? Well, with commas between. Our series is a sum of numbers. So there are plus signs in between the numbers. All right, and the very first example of a series that we looked at is the geometric series. And so as of right now, we know about the geometric series. And the geometric series is a series that's of the form the sum where I goes from 1 up to infinity of a r to the I minus 1. Now, your textbook, if you go and you read your textbook, sometimes they'll write this where instead of having an I as the incrementing value, they use an n. And so for some reason in section 8.2, they start with an I, and then they swap over to an n. And so another way that you might see this is as the sum where n goes from 1 up to infinity of a r to the n minus 1. So they just got tired of using an I and started using an n. All right, now when we write out the terms for this, either of these series that I'm looking at here, our very first term is going to be a times r raised to the 1 minus 1, so ar to the 0. So our very first term is a. Our second term, when I equals 2, will be a times r. And then we have ar squared plus ar cubed plus ar to the 4th plus dot, dot, dot. And this series goes on forever and ever and ever and ever. There are infinitely many terms in this sum. And so we have this sum, and then we can factor out the a. And we had a times 1 plus r squared plus r cubed plus r to the 4th plus dot, dot, dot. And so any series that we can write in this format where we have a constant out in front, possibly that constant is 1 if we can't really factor anything out, and then inside of the parentheses we have a series that starts with a 1, always starts with a 1, once we've factored out the a. The next term is the r value, and then r squared, r cubed, r to the 4th, and we go up by a power of 1 each time. And so this is our geometric series, and we went through this whole derivation last time and came up with this formula that said that if we look at the size of r, the absolute value of r, and the absolute value of r is less than 1, then the series converges. And what was really cool about this is that we actually get a formula for what the series converges to. The series converges to a over 1 minus r. And so I can look at this sum down here, and I can pick off the a value and the r value and plug it into this formula, and it will tell me exactly what this infinite sum of numbers is equal to. On the other hand, if the absolute value of r is greater than or equal to 1, then the series diverges. All right, now this is where we left off last time. We ended class and we looked at one example, and I'd like to take about 10 minutes and give you an opportunity to get your feet wet with an example where you're working with somebody in this class. So please take a look at the people around you. Say hello to them. All right, and I'd like you to pick at least one person, possibly more, and I'd like you to work together in a team for the next 10 minutes on an assignment that I'm about to give you, which means you might have to move your desk. Whether a sequence converges or diverges, and we talked about those in section 8.1. And then we have series, and a series is a sum of numbers, an infinite sum of numbers for an infinite series, so we're adding up a bunch of terms. Now, here's the problem. The problem is that when we're talking about a sequence, and we want to figure out whether a sequence, a list of numbers, converges or diverges, we have a list of limit tools, such as the squeeze theorem, L'Hopital's rule, highest power in the numerator versus the denominator, that kind of stuff. Those work for sequences. They do not work for series. So if you ever decide that you want to apply L'Hopital's rule to a series, you should slap yourself on the hand. Okay? So our limit tools for sequences need to go in a separate compartment in your brain from your limit tools and your converge versus diverge tools for series. Now our goal over the next few days is going to be to acquire tools for determining whether a series converges or diverges. So far, the only tool that we have is when a series is a geometric series. In other words, when the series can be written in the form a times 1 plus r squared plus r to the third plus dot dot dot. We have a tool for determining when that type of series converges or diverges, and what we look at is when the size of r is less than 1, the series converges to a over 1 minus r, and when the size of r is greater than or equal to 1, then the series diverges. This is the only tool that we have for looking at series, and there are plenty of series out there that are not in this form, where it's not possible to factor out one constant out of every single term and then have what's left over be 1 plus a number plus that number squared plus that number cubed, etc. And so we need to figure out, we need to learn a bunch of other tools to determine whether a particular series converges or diverges. Now, one thing that you might notice is that this is somewhat similar to, at the very beginning of the semester, we were hit with a whole bunch of integrals. And we learned all sorts of integration techniques and tools for finding antiderivatives. You want to kind of treat this in a somewhat similar way. We're going to be looking at series and trying to understand what these series look like, and then determine whether the series converges or diverges by using some particular tool. Okay, so that's our goal of the next few class periods. Okay, so what I just told you was we're going to be focusing on series. So I'm going to start with an example that's a sequence. So I want to look at the sequence AN, where AN is equal to N. So this is a sequence, and when I'm talking about a sequence, I'm talking about a list of numbers with commas between them. And so this sequence looks like 1, 2, 3, 4, 5, 6, etc. 3 dots at the end tell me that the sequence continues forever and ever and ever. Now, if I look at this sequence up here, as n gets really big, the limit as n goes to infinity of my terms, well, those terms keep getting bigger, and so my limit's equal to infinity, and so my sequence diverges. Now, if I take that sequence, 1, 2, 3, 4, 5, etc. And instead of having the commas in between, if I put plus signs in between, if I look at the series, that looks like the sum where n goes from 1 to infinity of n. What does this look like? This looks like, so here again, I'm going to transition over to using n's instead of i's. The reason that we use the i's with the geometric series is because we had that whole discussion about partial sums, and the partial sum as n went to infinity, etc. But here we're just going to start using n's. So, all right, n goes from 1 to infinity of n means that I have, my first term is 1, and then my second term is 2, plus 3, plus 4, plus 5, plus 6, plus dot, dot, dot. So now we are adding up an infinite number of terms. The terms are 1, plus 2, plus 3, plus 4, plus 5, plus 6. So take a look at that series over there. And without saying it out loud, I'd like you to decide, do you believe that this series converges or diverges? Okay, so now turn to your neighbor and tell your neighbor what you think. All right, so now that you've told your neighbor, you've committed to a decision. Raise your hand if you believe this series converges. Okay, raise your hand if you believe this series diverges. Okay, for those of you that believe this series diverges, does anybody have a reason why you think this series diverges? Can you explain why? Okay, yeah. As we add more and more terms, I mean, here we've got 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, 15, 21, 20. As we add more and more terms, this sum is just going to blow up in our faces. And so this series diverges. We keep adding larger and larger terms. All right, so that's fine. Let's look at another example of a sequence. So I said sequence, meaning I'm going to write down a list of numbers with commas between them. And so our second example is a sequence where an is equal to 0.02. All right, so if I write down my list, my sequence, notice that my formula for my sequence has absolutely nothing to do with the letter n, which means that when n is equal to 1, my value is 0.02. And when n equals 2, my value is 0.02. When n equals 3, I have 0.02. So every single term in my sequence is 0.02. So it's a pretty boring sequence. It's a constant sequence. So this is my sequence. Now, this sequence converges because the limit as n goes to infinity of 0.02, well, as n goes to infinity, absolutely nothing happens to this number, and so this sequence converges to 0.02. So it converges because our limit is equal to a number, and so the sequence converges to the number 0.02. Okay, so let's look at the series associated with this sequence. So if instead of just listing these numbers, if I add up, if I look at the sum, where n goes from 1 up to infinity, of 0.02, well, let's see, when n is equal to 1, I plug in 1 for n. Well, there are no n's over in my formula, so I just write down 0.02. And when n is equal to 2, well, I write down 0.02. So I've got 0.02 plus 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 0.02 forever and ever and ever. And so if I add up an infinite number of 0.02s, what's that sum going to be?
It's like putting two-cent deposits. If you make an infinite number of 2-cent deposits, eventually you've got some money in there.
Eventually you have an awful lot of money.
Yeah.
And so if you could live forever and put in your 2-cent deposit each day of the week from now off to infinity, well, you're going to be an infinitaire, billionaire, beyond a billionaire. You're going to have an awful lot of money. So in fact, you're going to have an infinite amount of money. And so this series diverges. Even though this number is very small, it's only 2 cents, it's only 0.02, if we add more and more of these 0.02s, the sum is going to continue to increase, and it will increase without bound. And so the series diverges because we are continually adding a constant value. All right, so there's two things I want you to notice about these two examples. In the first example, where our sequence, which I erased, but our sequence was an equals n, and the sequence diverges. In the case when the sequence diverged, well, it kind of made sense that if our terms in our sequence already were exploding off to infinity, then if we started to add all those terms together, that sum would also explode. And so it makes sense that if our sequence diverges, then the corresponding series, when we add all those terms, would also diverge, also explode off to infinity. Now in our second example, we had a sequence. Now our sequence converged to a specific number, 0.02. So the sequence converges, but the series, when we add up all those terms, the series diverges because we're adding more and more 2 cents each and every day. And so our series diverges even though our sequence converged. And so this particular observation has to do with something called the test for divergence. So it seems like it would make sense that if you have a sequence and that sequence does not eventually get super, super, super tiny, in other words, if our list of terms do not go to 0, then there's no way that if we add up all the terms that we're going to get some kind of finite number. And so this is what the test for divergence says. The test for divergence says if the terms of our sequence do not go to 0, then our series, the sum where n goes from 1 up to infinity, of all of our sequence terms, diverges. So I wrote a bunch of symbols up here, but if the terms do not approach 0, then the sum must diverge. All right, so this is the test for divergence. This is tool number 2. Tool number 1 is that you have, if you find a geometric series, you can identify that and identify the A and the R and figure out whether the series converges or diverges. Our next example is if we see a series such as the sum where n goes from 1 up to infinity of n over n plus 7. If I look at this particular series and I analyze the terms in my series, and so I look at the terms in the series, and the terms in this case are n over n plus 7, and I analyze what happens as n goes to infinity. If I look at the limit as n goes to infinity of n over n plus 7. Oh, by the way, at this point, I'm looking at the limit of a sequence, so I can use my sequence ideas in my head. So sequences, I can look at highest power in the numerator and denominator, and I see the highest power is 1 on the top and the bottom. So I can look at their coefficients, and I get 1 over 1, which is 1. And so since the terms in the series do not approach 0, instead they are approaching 1, since the terms in our series do not approach 0, the series diverges, and that is by the test for divergence.
So then right there, how do we know we could use that power rule? Because we started off as a series and then over there we went to this.
That's a really good question. So I'm analyzing the series itself. And that's my overarching goal. But in the process of analyzing the series, I want to focus on the terms in the series. So I'm focusing on the list of numbers that create the terms. And so I'm looking just at, I'm not going to be adding these things together. I just want to see what happens to the terms as n gets really big. And when I'm doing that, I'm thinking about a sequence. So once I analyze this as, so I'm looking at the terms in the series, aka I'm looking at the sequence, n over n plus 7. Once I start talking about a sequence, then I can use my highest power rule. All right. So, any questions about this particular example?
So even if, like you said, they're doing from the series, as long as it's looking at the terms in the series, you could use
That's
in
correct.
the sequence for the highest power rules.
That's correct. So once you take away the summation sign, and you're just looking at
The
the
limit,
formula that's part of your series, then you can talk about sequence
okay,
limits.
so like you read it into the formula, the limit, n equals infinity, then you do that.
Can you say it a little better?
So then you write into your formula like the limit,
Yes.
and then you do that.
Yes, that is correct. Okay, so there's our first example. Now, I do have a big caution for you. So here's a caution, and you want to make sure that you do not create this error, okay? And somebody will at some point, and if it happens to you, you should slap yourself on the hand, okay? Here's the caution. This test for divergence is a test to figure out if a series diverges. So in the case when the terms in the series do not approach 0, then we know that the series diverges. On the other hand, if we're looking at the sum where n goes from 1 up to infinity of an, and we want to figure out does this particular series diverge or converge, and we check that the limit as n goes to infinity of our terms, if we check this and our terms do in fact go to 0, that does not tell us that the series converges. If we check that our terms do in fact go to 0, then we know nothing. Okay. So this test for divergence is only fruitful if, when we look at the terms do not go to 0. If in fact the terms do go to 0, maybe our series converges, maybe our series diverges. Yeah?
So basically, all that does, that test for divergence, is it guarantees that you diverge.
Yes.
And then if it doesn't work, then you still might diverge, but then you have to check.
That's right. So if we do this test here and the terms do go to 0, it's possible the series diverges, but it's also very possible that the series converges. So, so we have to keep going. So this test is only valid, is only a useful test if your terms do not approach 0. If your terms do approach 0, this test, you want to throw it out the back door. All right. Any questions or comments about that? Okay, so that is test number 2. That's our test for divergence. So now I want to continue on into section 8.3. And this is something called the integral test. And I'm going to state the integral test, and then we're going to use it in a couple of examples, and then we'll see why this test makes sense. So here is the integral test. So the integral test says, let an be a sequence sequence of positive terms and suppose that an is equal to f of n, where f is a continuous positive decreasing function on the interval from 1 to infinity. Then the series, the sum where n goes from 1 up to infinity of an converges if and only if the integral from 1 to infinity of f of x dx converges. And the series, same series, sum where n goes from 1 up to infinity of an diverges if and only if the integral from 1 to infinity of f of x dx diverges.
So are those like exact things?
What do you mean by that?
There's no cautions for that?
There are no cautions on this.
So what's the point of the last week showed us?
The divergence theorem?
Yeah.
So here's the issue is that we're going to have series that we're not going to be able to write with, I mean, we have a couple of requirements. We need, for, so here we've got a list of dots, right? And we're going to add up all those values. In order to use this integral test, what we need to make sure of is that we can find a function that exactly matches our dots, and that function must be continuous. That function must always be above the x-axis. That function must be a decreasing function, meaning a function that's going downhill. So not every function, not every sequence can we do this. And so this test is not always going to work for us. It only works in very specific cases.
F of x and f of m the same function.
Yes, so this f and these two f's are the same. Up here I type in the n because it exactly matches. I want my function to work at the n values that I have, and then the f of x is the entire curve. Okay, so some things that, so one thing I just commented on is that we're going to need to make sure that our function that we have follows these three requirements: continuous, positive, and decreasing. And instead of analyzing a series, we're going to be analyzing an improper integral. So it's a good thing we talked about improper integrals earlier on in the semester. We're starting at 1 and going up to infinity. Now just sort of roughly speaking, this kind of makes sense, because when we're talking about a series, we're adding up a bunch of terms. And when we talk about an integral, we're adding up a bunch of rectangles. Essentially, we're adding up a bunch of terms. And so it kind of seems like there should be a connection between these two. Okay, so let's look at an example. So our first example is going to be the sum where n goes from 1 to infinity of 1 over n squared. So we want to figure out whether this series converges or diverges. In other words, as we add more and more terms, with adding adding each term, are we getting closer and closer to a finite value, or is our sum exploding off to infinity? Okay, so I look at this, and I look at the term in my series, the 1 over n squared, and that looks an awful lot like 1 over x squared. And so I'm going to look at the integral from 1 to infinity of 1 over x squared dx. So in other words, the function that we're looking at is f of x is equal to 1 over x squared. Now, in order to use this test, I better make sure of a few things. So first of all, our terms look like 1 over n squared, and so that totally matches up with our function over here. 1 over x squared is continuous, not continuous at x equals 0, but I don't care about that. I only care about the interval from 1 to infinity. So continuous. Positive, meaning 1 over x squared is always greater than 0. And decreasing. So if I draw a picture of this function, here's a picture of f of x equals 1 over x squared. Now, it looks like, yeah, from the y-axis and over, our function is going downhill. The left-hand side is not a decreasing function, but I don't actually care about that left side. I only care about from x equal to 1 and on. And from x equal to 1 and on, our function is decreasing. All right, so this is a valid choice for a function, and that means that if we evaluate the integral from 1 to infinity of this function and determine whether that integral converges or diverges, then we have answered our question about the series. Okay, so we now have our improper integral. Are there any questions about everything up till now?
I'm sorry, I missed why you canceled out the left side.
The left side, because I only care about these properties on the interval from 1 to infinity. And so I'm starting at x is equal to 1 and looking over this way.
Okay.
So yes, our function was increasing over here on the left side, but that's outside of the interval that we're interested in. Okay, other questions?
Based on the lecture you gave us about improper ones, those x being raised to the 2 there, it does mean that converges to a finite value. Are we going to analytically undo that?
So we're going to analytically undo it on this example, but you're absolutely right to be thinking ahead on that. Okay, so from our last time when we did these improper integrals, we actually evaluated this. So I'll do it relatively quickly here just to remind you about improper integrals. And so the very first thing that we have to do is to make this a proper integral. Take the limit as b goes to infinity of the integral from 1 to b of, and I'm going to rewrite this as x to the negative 2. Okay. So the very first thing is to take the infinity out of the bounds, and in order to do that, I replace that infinity with a letter, and then allow that letter to go off to infinity. Everybody, I hope, got this caution on the divergence theorem.
You're supposed to write that down.
Yes, that was an important thing to write down. Okay, so now we've got this limit as b goes to infinity, and we can take our antiderivative, so we will add 1 to the power and divide by that new power and evaluate between 1 and b. And so we have the limit as b goes to infinity of, all right, the very first thing I'm going to do is to fix this fraction so that it looks a little bit prettier, and I can rewrite this as negative 1 over x. I'm going to evaluate that between 1 and b. So we have the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. Alright, so cleaning this up, we've got the limit as b goes to infinity of negative 1 over b plus 1. I've cleaned that up as much as I possibly can. And now I ask, okay, as b goes to infinity, I'm going to take this to the limit. As b goes to infinity, this very first term, negative 1 over b, getting very tiny. So 1 over b goes to 0, and we're left with 0 plus 1, which is 1. Okay, so why are we doing this? Well, we are looking at this improper integral, and we did all of the calculus to figure out that our improper integral is equal to a finite number, so our improper integral converges. Integral from 1 to infinity of 1 over x squared dx converges. So, our series, the sum where n goes from 1 up to infinity of 1 over n squared also converges. Alright, so we did all this calculus work to figure out that our series converges. Now, here's a common hopeful question, and it's a very disappointing answer. Are you ready for this? So, when we calculate this improper integral, we determined that the area under 1 over x squared, starting at 1, and going off to infinity, that this area, if we want to paint this area, we need enough paint to cover 1 square unit, because our integral from 1 to infinity was equal to 1. That, unfortunately, does not mean that if we were to add up 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, that we would get exactly 1. So this number we get at the end here does not mean that our series adds up to give you this number. It just tells us that they're both going to do the same thing. They're both going to converge or they're both going to diverge.
So how do you figure out what it converges to?
That's a really good question. How do you figure out what your series converges to? And the answer to that is a very hard question that we will not cover in this class. We only get to do series converges or diverges, except for a geometric series, which is a super cool one because we know what the series converges to.
So does this relate to what you were just saying as far as where you have the sequence series that you just wrote up on the board?
Ask me that one more time.
Does this, what you just did right here on the board,
Yep.
does this relate to what you were just talking about where you had the sequence series? Where you were saying only valid term does not approach 0?
So that was our test for divergence. And so in this case, the integral test is test number 3. So the sequence does not go to 0 implies series diverges. That's a test by itself. And then this is a new test.
So you're saying that if this came out to be 0, that this would be saying that diverges?
No. So here, we're kind of thinking about here, when I look at my series, so for example up here, in this particular example, if I were to analyze just my terms, I can see that my terms go to 0, which means that when my terms go to 0, then that tells me nothing about the series, and I need to go on and do another test. And so in this case, because our terms, 1 over n squared, are going to 0, the divergence test tells us nothing. And so because of that, I have to throw the divergence test out the window. And I go on to a new test, which in this case is the integral test.
So what you were just explaining previously, you were saying that if you get that right up there, then you do a certain test. Is that what you're saying?
If these terms do not approach 0, then you can say by the divergence test the series diverges. But if these terms do go to 0, then we have to look at the rest of our collection of series tests, which at this point all we have is the integral test. Does that make sense?
I'll figure it out.
Okay, see if you can rethink the question and we'll go with that again. Okay, so try re-asking the question for the end of class. Okay, other questions?
So just because the integral doesn't go to infinity, we can say that the series converges, right?
That's correct, yes. Yeah?
In what class do you learn how to figure out what the series converges to?
Numerical analysis is one place that you can do that. So you can look at, and here we actually, so numerical analysis is the place where you're going to do that. We're actually going to do that a little bit in here. I fibbed a little bit to Will in the sense that we're not going to do this for these number ones, but eventually we're going to have series that add up functions, and we are going to see those functions converge to a particular function. So we will see it a little bit in here, but with the numbers we want. Okay, all right, these are all really good questions. Are there any more questions? Well, let's look at a second example of this integral test. I'm going to leave the integral test over there on the right-hand side. And here's our second example. And we're going to look at the sum, where n goes from 1 to infinity, of 1 over n. And the sum where n goes from 1 to infinity of 1 over n, maybe my first step would be to say, okay, is this a geometric series? And the answer is no, because with geometric series, your incrementing value is always part of the powers. So that's not the case. When I look at the terms, my terms look like 1 over n, and those terms go to 0, which means that my divergence test tells me nothing. And so then I look back at my series, and the question we're trying to answer again is, does this series converge or diverge? That's going to be the same question, so I probably won't end up writing this up here every single time. But we always want to ask, does this series converge or diverge? Okay, so I look at this and I say, okay, the test for divergence, the divergence test, does not tell us anything. So I look back into my toolbox of ways to look at series, and at this point, I have the integral test. So I look at this and say, all right, well, let's look at a function that looks awfully close to 1 over n, so probably f of x equals 1 over x would be a reasonable function to look at. And so I'm going to draw a picture of 1 over x so that I make sure I'm pretty familiar with it. Here's a picture of y equals 1 over x. And I need to make sure that the function I chose matches up with my dots that are created by 1 over n. And it does, because I've exactly replaced the n with an x. Okay? And our function f must be continuous on the interval from 1 to infinity. So I only care about this function starting at x is equal to 1 and going off to infinity. So our function is continuous. Check. Our function is positive. Our graph is always above the x-axis. Check. And our function is decreasing. So from x equals 1 and on, our function is always going downhill. So our function is also decreasing. Check. All right, so these are our 3 requirements, and that means that we can analyze our improper integral. And so we're going to look at the integral from 1 to infinity of 1 over x dx. Very first thing I'll do is make this a proper integral. So I'll take the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. after that, I now have a proper integral. I pay the price by putting a limit in the front. Take my antiderivative of 1 over x. What is that antiderivative?
ln.
Yeah, ln of x. And so we've got the limit as b goes to infinity of ln of x. Technically, it's the ln of absolute value of x, evaluated between 1 and b. So we've got the limit as b goes to infinity of ln of b minus ln of 1. And natural log of 1 is 0. And so we have the limit as b goes to infinity of the natural log of b. And so now the question is, as b goes to infinity, what happens to the natural log of b? And I might remember that this limit is equal to infinity, but if I wasn't sure, I could graph the natural log of x. And I know that this picture looks something like this. Okay, crosses at x equals 1. And this function continues to go up and up and up and up. So as b, or in this case x, gets really big, the graph of our function is getting higher and higher and higher. And so our limit is equal to infinity. And so our improper integral, the integral from 1 to infinity of 1 over x dx, diverges. So our series, the sum where n goes from 1 up to infinity of 1 over n, also diverges. Okay, any questions about that example? All right, so some things to think about here. First of all, this one should be a little bit unnerving to you, because this is an example. This series, the sum where n goes from 1 up to infinity of 1 over n, is an example of a series where the terms of the series approach 0. In other words, 1 over n goes to 0, but the series itself, the sum where n goes from 1 up to infinity of 1 over n, when you add up all of these terms, then you actually get infinity. So the series itself diverges. So this is an example where the terms of the series do go to 0, but when we add up all the terms, we get infinity. And this particular series, this exact series, the sum where n goes from 1 up to infinity of 1 over n, which if we write it out is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus etc. This series has a name, and it's called the harmonic series. And the harmonic series is a great example of a lot of different things. So this harmonic series you want to keep in your back pocket. Okay? We've got a summation sign, we've got a 1 over n, and the terms themselves go to 0, but the sum diverges. Okay. Are there any questions about that example? All right, so I want to wrap up with giving you an example I'd like you to look at for next class. So for next class, like you to use the integral test to determine whether the series converges or diverges for the following two series. The sum, where n goes from 1 up to infinity, of 1 over n raised to the 0.9 power, and the sum, where n goes from 1 up to infinity, of 1 over n raised to the 1.1 power. All right, so I'd like you to use the integral test on those, and then I have some practice problems. So we're going to talk about these two examples at the beginning of class next time.